Hey chemistry! So today we are going to start chapter 14, which is all about gases. I will warn you, this chapter does have a lot more math in it than the last one, but it's a different type of math. It's more just equations, figuring out what you have, what you need, and then being able to plug and chug, so you'll be okay. Today we're going to go through 3 of the gas laws, so 3 equations that we'll talk about. But first we have to rediscuss kind of kinetic theory. So, the kinetic theory assumes the following concepts about gases. 1. Gas particles do not attract nor repel each other. So gas particles are free to move around without interference from other particles. 2. Gas particles are smaller than the distances between them. So you have a lot more space between the molecules. Gas particles themselves have virtually no volume. Almost all the volume of a gas is empty space. Okay? 3. Gas particles are in constant random motion. Gas particles spread out, they mix with each other, they're constantly moving, and it's random. It's not a pattern. 4. No kinetic energy is lost when gas particles collide with each other or with the walls. So these are all elastic collisions like we learned about last chapter. And then 5, all gases have the same average kinetic energy at any given temperature. Okay? So, actual gases don't obey all the assumptions, but for many gases, the behavior approximations do go with these assumptions, okay? All of them are based on the number of particles present, the temperature, the pressure, and the volume. Those are your 4 variables: the number of particles, temperature, pressure, and volume that we're going to be working with this chapter. Think about a plastic balloon. If you have a plastic balloon and you squeeze it and you temporarily decrease its volume, what happens? The amount of gas is constant because no gas can escape the balloon unless you push too much and it pops in your face. But if the temperature is held constant, decreasing the volume is going to have to increase the pressure. And this happens because your number of collisions between gas particles per unit time is going to increase. They're going to be more likely to run into each other because they have a smaller space in which to move around. So that's kind of what Robert Boyle came up with when he created Boyle's law. He was an Irish chemist. He did experiments like that to study the relationship between pressure and volume. He took very careful measurements, realized that they're inversely proportional, which means as one goes up, the other one goes down. As the volume goes up, the pressure goes down. As the volume goes down, the pressure goes up. Make sense? So Boyle's law is pressure 1 times volume 1 equals pressure 2 times volume 2. This chapter is going to be a lot of understanding which equation to use when, how to plug and chug. So these are, your pressure 1 and volume 1 are your initial conditions. Pressure 2 and volume 2 represent the new conditions. So pressure 1, volume 1 is going to be how, whatever it starts at, and pressure 2, volume 2 is going to be wherever it goes. Okay? So let's do an example problem for how to use this. A sample of helium gas in a balloon is compressed from 4 liters to 2.5 liters at a constant temperature. It's important. If the pressure of the gas in the 4-liter volume is 210 kilopascals, what will the pressure be at 2.5? All right, so we were given pressure 1. We were given volume 1 first. Okay, so volume 1 equals 4 liters. Volume 2 equals 2.5 liters. Pressure 1 equals 210 kilopascals. So we just need to figure out pressure 2. So we plug it in. Pressure 1, 210 times 4 equals 2.5 times P2. 210 times 4, I need my calculator, it's going to be 840 equals 2.5 P2 divided by 2.5 divided by 2.5. Calculator. 336 kilopascals. Sometimes can be rounded. Okay, so, yes, 840 divided by 2.5 equals 336. So, this is going to be our answer. All right. Your book says 340, but that's just because they rounded it. That's all that is. I don't know why they rounded it. They just did. Okay. So that is kind of an example. You figure out your initial conditions. You figure out where it goes. You plug it. You chug it. Okay. Let's do one more example. So I'm going to erase this one because we have a lot more laws to cover today. All right. So now we're going to do example problem 1 on page 422. The volume of a gas at 99 kilopascals is 300 milliliters. If the pressure is increased to 188 kilopascals, what will be the new volume? All right, so we have initial volume is 300 milliliters. Initial pressure is going to be 99 kilopascals. Second pressure, it says it moves to 188 kilopascals, and we just need to know what volume 2 equals. So, plug it in. 99 times 300. Now, no, these are different units than before, but as long as they're consistent from 1 and 2, doesn't matter what units you use. So 99 times 300 equals 188 V2. So, 99 times 300 equals 29,700 equals 188 V2 divided by 188. That equals, we'll round it to 158 milliliters. And that's going to be our answer. All right? So those are your example walkthroughs of Boyle's law. With that said, let's turn to Charles' law. All right? So I'm going to erase this. Pause it if you need. And now let's talk about Charles. So, have you ever noticed that on a cold day, a tire on a car might look like it's low on pressure? Also, your low tire pressure warning might go off in your car. But after driving, the tire warms up and looks less flat. What's the difference? Well, gas temperature and volume are going to be related. Jacques Charles, so Charles was his last name, studied the relationship between volume and temperature. He observed that as temperature increases, volume also increases. So this is going to be a direct correlation, not inverse. Okay, so you've got a graph on page 423 of volume versus temperature, and it's direct. As one goes up, the other goes up. So Charles's law, the equation is going to look like this. Volume 1 over temperature 1 equals volume 2 over temperature 2. All right. V and T1 are the initial conditions. V and T2, where it goes to, just like before. Let's walk through an example. So a gas sample at 40 degrees Celsius occupies a volume of 2.32 liters. If the temperature is raised to 75 degrees Celsius, what will the volume be, assuming pressure remains constant? That's the one thing about these gas laws, is that means nothing else can change. If your temperature, your volume, and your pressure both change, or all change, you can't use these. You can only use these when these two things are the only ones changing. Okay? When we get to more than one or two things changing, there's different equations for that, which we'll learn about Monday and Tuesday. But for now, just focus on when only two things change at once. Okay? So, the example again, let's see. Initial temperature equals 40 degrees Celsius. Initial volume equals 2.32 liters. If the temperature is raised to 75 degrees Celsius, then what does volume 2 equal? All right, so volume 1, 2.32 divided by 40 equals V2 over 75. So we can start with the one side, 2.32 divided by 40. That gives us 0.058 equals V2 over 75. So to get rid of that, we multiply both sides by 75. I do apologize. I forgot one step. So, go back. According to the gas laws, the temperature scale must be expressed in Kelvin units. We've talked about Kelvin before, But Kelvin starts at absolute zero, which corresponds to negative 273 degrees Celsius. Because a Celsius degree and a Kelvin unit are the same size, it's very easy to convert. All you do is you add 273. Okay? So, temperature in Kelvin equals temperature in Celsius plus 273. Alright? So, in that case, let's convert a couple things. So temperature 1 over here equals 40 plus 273 equals 313 Kelvin. Temperature 2 equals 75 plus 273 equals 348 Kelvin. I do apologize about that. Alright, so now let's use our adjusted. Now, when you do solve these, you're going to want to, for the most part, present your answers in Celsius, because presenting answers in Kelvin doesn't really mean anything, but you're going to need to use Kelvin for the actual calculations, okay? So, let's try this again. 2.32, volume 1, over 313 equals an unknown volume 2 over 348. Alright, so let's do that again. 2.32 divided by 313 is 0.007 equals 2 over 348. Multiply by 348 on both sides. You end up with 2.58 liters. Alright, so that's going to be an example. And no, you would not have gotten the same answer if you'd done it in Celsius. Okay, just so you know, you do have to convert to Kelvin. Alright, so this is one example. Let's walk through a second one. I'm going to erase this so we have some more space, but we are going to walk through one more example. Alright, so this is going to be example problem 7 on page 425. Alright, so the Celsius temperature of a 3-liter sample of gas is lowered from 80 to 30. What will the resulting volume of this gas? Alright, so we've got volume 1 is 3 liters. Temperature 1 equals 80 degrees Celsius, but we do have to convert to Kelvin, plus 273. And that's going to give us 350, 30. We do not know volume 2, that's what the problem asks for, but temperature 2 is given to us. It's been decreased to 30 degrees Celsius. So 30 Celsius plus 273 is going to give us 303 Kelvin. So now we can plug and in. So volume 1, 3 liters divided by 353 Kelvin equals volume 2 over 303 Kelvin. So, here we go. 3 divided by 353 equals 0.0085 equals V2 over 303 times by 303 on both sides. And 2.58 liters is going to be our volume 2. Alright? So, those are 2 examples of Charles' law. Now, we have one more law that we are going to talk about today. And then your Juno plot has practice problems for all 3 of these laws. And the last law we're going to talk about today is relates pressure and temperature. So Joseph Gay-Lussac, it's French, it's probably pronounced with a fancy French accent, but I don't have one of those. It states that the pressure of a given mass varies directly with temperature. So the higher the pressure, the higher the temperature. Another direct relationship. So that is, since Charles's law was also direct, this is also going to be a dividing equation. Boyle's law was inverse, and so that's why it's a multiplying equation. So Gay-Lussac's law. We're going to have pressure 1 over temperature 1 equals pressure 2 over temperature 2. Alright? So let's walk through using that. The pressure of a gas in a tank is 3.2 atmospheres at 22 degrees Celsius. If the temperature rises to 60, what will the gas pressure be? All right, so we've got temperature 1 equals 22, but that's in Celsius. We have to convert to Kelvin. 273 equals 295. Pressure 1 is 3.2 atmospheres. Temperature 2, the temperature rises to 60 degrees Celsius plus 273 gives us 333 Kelvin. And of course, we don't know pressure 2. So we have everything we need. Let's plug it in. Pressure 1, 3.2 divided by 295 equals pressure 2 over 333. So 3.2 divided by 295, going to be another very small number. Alright, so we end up with 0.011 equals pressure 2 over 333. Multiply that by 333 on both sides. This cancels out. Times 3. We end up with 3.61 atmospheres is going to be pressure 2. All right. So that's the idea. Let's do one more example problem. Give you a moment to pause that if you'd like. And then, here we go. Okay. So now we're going to do number 9 on page 427, and this is the last thing we're going to do. All right, so a gas in a sealed container has a pressure of 125 kilopascals at a temperature of 30 degrees Celsius. If the pressure in the container is increased to 201 kilopascals, what's the new temperature? All right, so initial pressure is given to us in the equation is 125 kilopascals. And the temperature was given to us as 30 degrees Celsius, but we have to convert that to Kelvin, so plus 273 equals 303 Kelvin. All right, now the pressure is increased to 201 kilopascals, so that means that pressure 2 is going to be 201 kPa, and we do not know temperature 2. So let's plug and show. 125 over 303 equals 201 over temperature 2. All right, so 125 divided by 303 is 0.413 equals 201 temperature 2. So now, in theory, what we would do is we would multiply by temperature 2 on both sides. So then we end up with 0.413 T2 equals 201, which means we can just divide by 0.413. And we end up with 201 divided by 0.413. End up with temperature 2 equals 487 rounded Kelvin. So now to figure that last one out, we do need to subtract 273 to convert it back to Celsius. So 487 minus 273 gives us 214 degrees Celsius. I did round, but you are allowed to do that too with numbers that big. All right? So remember, all your temperatures have to be in Kelvin, but other than that, your 3 laws for today are these 3 simple kind of math things. And yeah, so hope that helps. Enjoy, good luck, and next week we will continue on. Bye guys.